Hey all, it's Andrew Couch here. In this TidyTuesday video, we're actually not going to be looking at this week's data set, which is on astronauts. Instead, I was actually reading a textbook this weekend, and it was the Interpretable Machine Learning, a guide for making black box models explainable. And I'll put the link in the description below. But basically, the main idea behind this entire textbook was describe methods on how to create some inferences of why your models are predicting these actual predictions. And that's kind of the big problem with these black box models. Although you have a lot of predictive power, you're also sacrificing interpretability. Whereas with logistic regression, linear regression, and other generalized linear models, you're basically sacrificing predictive power for better interpretability. So in this textbook, they just show you kind of ways to still use these models with high predictive power, but also be able to increase the interpretability by it. So we're just going to do that. I'm going to load up a R Markdown file. R Markdown. And we're going to call this TidyTuesday Black Box Models. Okay. So I'm going to delete this garbage. And we're going to load in the Tidyverse, Tidy Models, the Ames Housing, the Broom package. And then we're going to load in the IML package. So the Tidyverse is going to be for our data manipulation. Our Tidy Models is how we're going to make the actual models. Our Ames Housing package is going to supply the data. The Broom package will also do some of the data manipulation, specifically for cleaning up our models. And the IML will really show, will be the kind of the main package where we're going to be doing the interpretation of these black box models. So with Ames Housing, we can actually just say, we'll call this Ames DF, and we'll say make Ames. And then we can just do a basic look at it. And it's the thing that we've used this data set before. If we do a glimpse on it, we can see that there's 81 columns with about 3,000 rows. What I'm actually going to do is I'm going to select only the numeric ones, just so we can do better interpretations of the values. Select. So I do a select if is dot numeric select is dot select if what is dot numeric. Okay. Additionally, with Ames Housing dataset, you're gonna have to select the sale price, and then I'm gonna say everything, just so it's a little bit cleaner. So we have the first column as the variable that we're trying to predict. Okay, so we're gonna do that, and I'm gonna assign that to a to itself, to the Ames DF. Okay, so when we look at the actual thing, the actual textbook, one of the main ideas behind it is just kind of using linear models to describe your data. So let's first just make a baseline linear model where we're going to predict the sale price using all our predictors. So that's it. You know, pretty quick, takes about 2 seconds to make a linear model to predict sale price. If we do the tidy function, so if say linear model tidy, we can kind of get our terms, our estimates for the coefficients, standard error, p-values, you know, the generic linear model stuff. And so when we use a linear model, we're trying to interpret it. A common plot that we use is called like a coefficient plot. So if we just say like x equals term, y equals estimate, plus geom like column, and then we just maybe do a chord flip. Oh, geom, what is it? Geom point. Let me just do a filter. So I'll say, or maybe we can do a slice -1. Yep. So we remove the intercept, and we can see how we can look at our estimate, yada yada. Additionally, we can also say, was it conf.int equals true? I think. Yeah. So if we do that, and then we do, so if we do conf.int, we get our conf high and low. So instead of doing geom, we can also do a geom, point range, as yn equals, wait, what? It's y min equals conf.low, y max equals conf dot high. And then we can kind of get some conf intervals with our estimates. But there's a huge problem with this actual plot. So although we're seeing our coefficients, so in a visual manner, so if we actually just do the table, here's our coefficients, nothing too crazy. But if we look at our coefficients, we can see that, actually, let me do another thing. Plus scale with x log 10 or scale y log 10. We can see our coefficients. It's not really a great introduction of how we should be looking at it, because if we look at years sold, let me see here. So years sold may have like a 0, or if we look at, say, lot area has like a coefficient of like 0.9, right? So if we just do that. So if we go to like lot area, it's 0.3, compared to lot frontage, which is 87.375. So if we naively looked at these coefficients, we would say, okay, year remodel add and lot frontage, those are the biggest things that we need to look at. Or basement finished in whatever area 1, that's our best coefficient. But they're on different scales. So for example, lot frontage or lot area has a small coefficient, but the area is probably going to be on a much larger range, right? Or just a larger scale compared to, say, year remodeled added, right? So you might have a lot area of like 300 or 3,000, but it's really rare to have a year remodel added to be like, 3,002. So this is just a coefficient plot. But what we want to do is actually basically multiply our values for each term times its estimate, and then look at its actual contribution to our sale price. And what that is called is an effects plot. So let's say create an effect plot. So we're basically for every term, we're multiplying each sample by its estimate for each term. Okay, so we're basically calculating each marginal effect for each estimate. Okay, so let's do that. And that's why we're actually going to use the tidy function. So if we do a tidy, we have our terms. We don't really need our intercept, because every term will receive that same intercept. It's essentially the average. So what we're going to do is we're going to say select term and estimate. Okay, and we go to our aims data. What we can do is just do a mutate, and we'll say primary key is equal to row number, because each row is a house or a sample. And then we can do a gather and say key equals key, value equals value, and then minus, I guess we don't really need sale price, but we'll say minus, just that. Let's see, let me think. And then we'll just say minus sale price. Okay, so here's our, minus sale price, and then we'll say minus PK, right? And then what we can do is we can do a left join. So we're essentially saying we're going to join by the key. So that way we'll have our coefficient for all these samples. Okay, so left join this. I'll clean this up a little bit. So, and then we'll say by equals C, and we'll say, what's it? Key equals term. By equals C. Oh. Okay. So what we can see here is like, here's our first sample, its corresponding feature, its value, and then the actual coefficient for it. So what we're going to do is mutate and we'll say effect is equal to value times estimate. Cool. And that's basically it. So now we can just do a ggplot, x equals key, y equals effect. And then we can do like a box plot, and then we'll say plus a chord flip. Okay, so one other thing that we should do is probably scale it. So one thing I want to do is like a log 10 scale, a log 10 transformation. However, we have negative values for the negative coefficients. So what I'm gonna actually do is I'm gonna make sure to do this. So I'll say, I'll create a pos neg value. So it'll be an if else effect is less than or equal to 0, then it'll be a negative, and then it'll be positive, and then I'll change effect to the absolute value. Okay, and now I can just say color equals pos neg. Cool. And then I'll do a plus scale y scale x log 10. Scale plus scale scale y log 10. And there we can see how our plot is a little bit different compared to our effects plot. So if we look at our effects plot, we can see it's all scattered. In reality, for here, we can see that the thing that adds the most contribution is actually longitude and latitude for a positive, to increase your sale price in your house. If we look at the negatives, we can see open porch. So those have the negative contributions towards it. Okay, so that's just kind of a quick way to view the actual effects of the plot. So I'm going to say create an effect plot. Well, so now that we showed like just kind of how you interpret some linear models, or how to make some plots to analyze your linear models, I'm actually going to start making some black box models. So I'll say this, like start making some non-interpretable models. So what I'm going to do is I'm going to create just the baseline for a random forest model. So that'll be a random forest, set mode to regression, and I'll set the engine to random forest, and I'll also do a XGBoost model, because these are kind of the models that most people view as like non-interpretable models that are also very popular. So set the engine to XGBoost, XG set mode boost tree set. Oh, set engine. There you go. So I have these models that are just here, but what I'm going to do is I'm just going to train the models, or train and create train models. I'm actually not going to do any tuning for it. I'm going to use the baseline parameters. So I'm going to say set.seed 42, and I'll just say random forest model, and I'll say fit, and then say sale price data equals aims df, and I'll say XGB model is equal to the XGB model, and I'll fit it just to its values, fit it to the data. So it's sale price data equals aims df. And when I do this, it's actually just gonna run it with the default parameters. So there's some default parameters for random forest XGB that they'll just kind of use as like basic basic starting points. So I'm gonna start training these models. Okay, I think I actually created them, right? Okay, we got that. GP model. Cool. So we trained these models. It was pretty fast because we weren't doing any cross validation. I would definitely say that we might have overfit or underfitted the model, but this isn't really about how to optimize your model parameters. It's more about how to use and interpret these black box models. So with the IML package, this is the package that basically shows how to interpret these black box deep learning models. One of the main things is like feature importance. So what we can do first is we have to kind of give it the actual model data. So I'm just going to do that. So select and then say minus sale price, and then it takes it as a data frame. So we have our X data, and now we can create our actual models that it can kind of like test on. So we're going to create two different models. One for our first random forest model. So we call it RF predictor, and then you give it the predictor, and then you have to say the $ or new, give it the actual model, give it the data, the model data, which is X data, and then give it what we're actually trying to predict. which is sale price. Okay, and then we just do the same thing for the other model. So XGB predictor, predictor new, and then was it XGB model data equals X data and Y equals aims df sale price. Cool. So let's just do a feature importance plot. So I'm gonna just say RF feature imp, and we'll say feature imp new, and then we give it the RF predictor, and we can give it a loss function. So see how each predictor impacts a specific loss. And when I'm trying to communicate how models model performance, it's best to communicate in the most simplest metrics when doing presentations. So I like to train models to optimize off of root mean squared error. However, it's not very it's pretty hard to wrap your head around the root mean squared error when computing like average loss. So I think the best metric when communicating towards other people is mean absolute error, because you can essentially say that, okay, our model on average when it predicts, it's wrong by this much, right? So on average, each time it predicts the sale price is off by about $200. Instead of saying root mean squared error, which is like the square and then the square root of it, it's very confusing, and it's not a good way to really communicate to people. I'm also gonna build it with the XGBoost model. So one of the big things with these interpretability things is it does take a decent amount of time to run it. So I'm going to let that go. And we're actually going to go over feature importance. So most model diagnostics or modeling libraries will always kind of have a feature importance. And this essentially shows what features, when it removes, has most impact on performance. So in this case, when we're looking at this, we're saying like, okay, so with all of the aims data, so for all of these features, if I remove years sold, how does that impact the mean absolute error? Okay. So what we can do now is we can do the RF feature imp, and then I think we can just plot it, and we see right here. So it's saying that when it removes GR live area, which I think is great living area, maybe, or something like that, we can see that it has a huge loss in predictive power. We can also see the year built is a huge indicator of the sale price, or total basement per of square foot versus 4 square foot. These all make a lot of sense for how it's looking at when it's making predictions on sale price. We can also look at the XGBoost feature importance. Actually, I'm going to do it separately. So what we're actually going to expect when we're interpreting these two models is we kind of want the main feature importance to be the same if we're kind of looking at robust models. However, if you're like ensembling models or doing some stacked model framework, it's actually kind of good to have models who have different feature importances. But that's probably for another video. So when we look at these two models, we can see that both XGBoost and RandomForest put a huge emphasis on RandomForest, on a great living area. Additionally, they have total basement on square foot and year built on the top 3. They're interchangeable. You swap them around, but it still shows that the main 3 features that they use for evaluating sale price is the living area, year built, and total basement for of square foot. Cool. So that's a pretty simple plot, but it's not really a thing that goes too deep into the actual understanding of how models work. So another good thing that the IML package comes with is the feature effect function, which plots out the ALE and ALE plot. Which the ALE plot, let me look it up. It's the it's kind of a weird word. Let's see here. It's called the accumulated local effects plot, and it basically tries to find how the features influence on average. And one of the main things that differentiates this plot with a bunch of other plots, so another plot that you would probably hear of is the partial dependence plot. The partial dependence plots has a main has a main assumption where it assumes the features are uncorrelated. Oops, you saw my thing, are uncorrelated and independent, which is actually really bad for most models. So one of the main reasons why people do black box models is that they can use highly correlated features or not independent, or not independent or dependent features. So what does this really mean? It basically means that if you're using a PDP plot on our features right now, which we know that if I just do a basic correlation analysis, so AIMSDF core, and then just do a core, we can see that it's definitely has some correlated features. So for example, one of the things that's a good example of correlated features is like height and weight. So the higher, the taller you are, the more you're gonna weigh. Since a PDP plot would assume that's uncorrelated, it'll basically try to test all these features in the feature space. What that means is it'll basically show, or it'll basically plot out samples where a person is like 2 foot tall but weighs 300 pounds, which is unrealistic to see in the wild. Which is why people use the ALE plot now, or accumulated local effects plots. And basically the rule of thumb when I was reading the textbook is you should basically always use the ALE plot before PDP plots. So that's why we're going to do the ALE plot. I'm also not going to go into the math of it because I don't think this is really out of the scope of the video. And I think the ALE plot should just it's more fun to just kind of interpret the ALE plots. So that's what we're going to do. I'm going to do RF ALE and say feature effects. And then we'll say new, and we'll say RF predictor. You can also change it to feature effect, and then you can specify the predictor. But in this case, I want to kind of look at every feature and its impact when predicting. We're also going to do the XGB ALE. So feature effects, new, and then XGB predictor. Oops. See, so it says feature is missing because I said feature effect instead of feature effects. Cool. I'm gonna take a sip. Okay. And what's cool again with the IML package is you can just plot it out. We're gonna wait for that. Okay, so it's not looking good, so I'll do fig.height equals 15, fig.width equals 15, just to make it a little bit larger. I'm also going to copy this code chunk, paste it right there, and then do the XGB ALE. So that way we'll plot both, and while the XGBoost plot is plotting out, we'll be looking at the RandomForest plot. Okay, cool. So what this plot shows is basically the distribution of each marginal effect. Not each marginal, each average effect from each feature. Okay, which is pretty useful. Okay, so the y-axis is saying like how are you predicting sale price, and we can see how okay, when we increase our lot area from like 20 to 100, we can see we have a huge increase in sale price. But then the actual rate of increase in sale price starts to diminish. However, we can still increase as it goes. There's no actual hump shaped distribution of it. See again with a GR live area, we can see how a GR live area is just has a high slope in general. Additionally, if we look at the x-axis, you can see how there's darker lines. These are called rug mappings or whatever, and it shows the density of most of our samples. So most of our samples and the lot frontage are in like the 0 to 100 range. And you can see our year built, most of these houses are basically newer houses or made after the 40s or 1900s. So this is probably one of my favorite plots when I'm trying to interpret these machine learning models. But it shows like each feature's effects and kind of like the simple curve of it. Because it's really hard to actually visualize like three-dimensional effects. Instead, they just kind of show these like faceted plots of each marginal effect on average for the distribution. We can also look at the bottom, the XGBoost model, and see it's kind of showing the same thing. We see how the GR live area has a steep slope, and it's good. So when we're actually showing these models, then a lot of times you might get questions on saying like, okay, we have these models, we know how it's reacting to this entire data set, we know why it's looking at this data and why it's kind of making these predictions. But one of these things that you kind of need to know is, how can we, how can like when your model does a prediction, we kind of want to see like, okay, what things do we need to change the prediction. For example, in the book that they used, in the book, they're talking about credit card application. So we have a machine learning model that basically looks at like your payment history, your gender, your age, and they get rejected for a credit card. They probably want to know why, what contributing factors contributed to them failing their credit card application, which that involves the Lime model, which is like local. Let me look up the name of it. It's what is it? It's called the local surrogate models, and it's probably one of the most popular. Probably one of the most popular models that they use for interpretive modeling, and it's mostly just for analyzing individual predictions. So it's like for analyzing how models make individual predictions. Okay, cool. What's kind of funny, there's so much research about Lime models or local surrogate models. However, actually implementing the Lime model is pretty easy. So I'm just do RF Lime, and we'll say local model, new, and then RF predictor. But we have to give it our X interest, which is the sample that we kind of want to look at. So we'll just say X data, the first the first data point. Okay, and if we actually plot the RF Lime, we can see what the model was looking at. So it says the main reason why it made the prediction of $200,000 was because of your GRO living area, which had the largest effect to your contribution of a home sale price. Additionally, it said that since you had a 2-car garage, that had a $10,000 contribution to it. Additionally, their total basement of square foot was 1,080 total square foot. And now we can also look at it for the XGBoost model too. So we'll say XGB Lime, local model, new, XGB predictor, and then X dot interest, X data 1. Okay. And then we can plot that out, and let's see what it was looking at. So again, when I was looking at, so this is with the same house, and it basically used the same predictions, and it shows the same contribution effects. In this case, the XGBoost model actually puts a less effect on the GRO live area. Additionally, it has a larger increase in the garage cars, or the two-car garage. So that's basically it for this video. I wanted to make a shorter one because I just read this textbook and I thought it was a pretty interesting read. And I think a lot of this stuff is pretty simple to implement, and you can kind of just go to town and go crazy with it. I think in the future, I might implement a Lime model in some type of text generation or text NLP model and put that in a dashboard, but that'll probably be for future videos. So yeah, that's it. And I'll see you next week, and tidy on.